Hey everyone, welcome back to our channel After School. Welcome back to our revision session 2. So guys, how are you all? So today we are going to discuss revise the chapter that is refraction of light at curved surfaces, right? So let's discuss what are the important and no, what all are the topics in this chapter. So first, refraction at curved surfaces. So it says that if it going from denser medium to rarer medium and rarer medium to denser medium and through the surface too, if the interface is the concave medium, concave surface, and if it is a convex surface. Okay, we will discuss here four cases how the light ray bends. Fine. And after that we are going, then we will discuss curved surface formula. In the chapter there is a derivation of this formula, but since it is a revision revision, so we will only discuss the formula and the terms. And after that, the main important part of this chapter, that is spherical lenses. After that, how these lenses forms and what are the main important terms like optical center and center of the curvature, then focal length, focus. So we will discuss all these terms. After that, focal plane. What exactly is focal plane? When the image forms on this focal plane. Okay, how and after that, behavior of lenses. Light rays on lenses. If the light ray is perpendicular to, I mean, parallel to the principal axis, then how light ray, refracted ray bends. If it is passing through the center of the curvature, okay, center of the lens, then how refracted ray bends. So we'll discuss these cases, four cases here, four cases are there, we'll discuss here. And image formed by concave lenses and also convex lenses. Then we will discuss ray diagrams. Okay, after that, uses. And after that, these three formulas are very important because we can expect numerical problems on these three formulas. Okay, and also this too. Got it? Now without wasting time, let's get started into the topic. So here we are going to discuss when the refraction of light, refraction through a curved surface, when the interface is here it is convex surface, convex surface, and here it is concave, right? Now it is air medium, that means rarer medium, and it is this colored surface, you can consider it as any denser medium. Okay, so here I'm mentioning it is a denser medium. Fine. Okay, now here I'm just drawing a perpendicular line. Okay, and now light ray is coming parallel to this line. Then what happens when it is intersect on this convex surface? Then the light ray refracts, right? But how it refracts faster? Wait, it is coming from air medium, that means a rarer to denser. Okay, when the light is coming from a rarer to denser, then light ray, refracted ray bends towards the we do have two cases. It is bends towards the normal or away from the normal. Since it is going to the denser medium, it bends towards. Okay, and if it is a rarer medium, then it goes away from the center, right? So for this curvature, if I am considering this is a center, then for this point, what will be the normal? So this will be the normal. Okay, so this will be the normal. Now the light ray goes from, how it goes, it is towards the normal, right? So it bends like this. Okay, and the same case here too we are considering a line. Okay, now a mid line. Now here the light ray is going from the, again this case is rarer to denser, right? Okay, let's just consider that it is incidenting on the surface like this, but it incident on a which surface? Concave surface, right? it is a concave surface, then what happens, how it bends? Anyway, this is to bends towards the uh, let's see whether it bends towards the lens or not. So yes, it is going from rarer medium to the denser medium, right? So anyway, here to bends towards the uh, normal. So here, what is the normal? So it is the center, sorry, not this. Center will be on this side, right? So this is the center. Fine. If I just draw the normal to the surface, then to the point of incidence, then it will looks like this, right? So this is the normal at this point. Now the refracted ray bends towards the junction, sorry, towards the normal. So this looks like, okay. So this is the ray. Fine. So this is the two cases when light ray incident when light ray is going from a rarer medium to the denser medium and intersecting at a convex surface, and this is concave surface. Now next case is that now the light ray is going from denser medium to the rarer medium. Now this is the denser medium and it is the rarer medium, and light ray is coming from this side. Okay, let's see how it bends. Now let's just take a line like this, and on this line I'm just taking the center of this curvature. Okay, now center will be here and line ray is passing like this. Okay, now light ray is incidenting on this like this. Now at this point it is changing its medium, right? Now it is entering to the rarer medium. In this case, how the refracted ray bends. So here we since we have discussed it in the last revision, last slide, that is, if it is a rarer to denser, then it bends towards the normal. But if it is denser to rarer medium, then it bends away from the normal, right? It bends away from normal. So here, what is the normal here? Okay, let's draw the normal. This is the normal. Fine. Now it bends away from the normal, right? Now the refracted ray looks like bends like this. Fine. And the same goes for the other part as well. Now here too, I am taking a line. Okay. I'm considering a line like this, and on this I'm just locating the center for this curvature. For this curvature, center will be located here, right? So it is C, and the light ray is going from denser to the rarer. So I'm just considering the light ray like this. If it is going like this, then it intersecting at coinciding this surface. So what is this surface? Concave surface, right? Sorry, it is the convex surface. So this is convex surface, and here it is concave surface. Now on this concave surface, if we just draw normal at this point, then it looks like this. Simply we just need to draw the radius from this point. Okay, now this is the normal at this point. Now how the refracted ray bends? So it bends away from the normal. So it looks like this. So this is the incident ray and this is the refracted ray. It is the incident and it is the refracted. And here too, is in last session also I have mentioned that whenever you are drawing the ray diagrams, you should mention the direction of the ray, like from where to where it is going. So these are the four cases of light ray bending while it is going from denser medium to rarer medium and coinciding at on the surface, whether if it is a concave or convex. Now let's see the curved surface formula. So curved surface is nothing but simply here we are just considering a curved surface. Okay, so this is the curved surface we are considering, and yes, it is a medium. Okay, here too we are just considering a line. Fine. So this is the line. Now when we place the object here, then what happens from this point to here? This is known as object distance, right? Object distance u. When it forms the image on the other side, okay, let's say here it formed the object, right? Image, right? So this is image, and this distance is known as v, because it is distance from origin or a pole. We can consider it as a pole to the image is image distance, and pole to the object is object distance. We have described it, we have represented it with u and v. Now the refractive index of this medium is n2, and when light ray is going from this medium to that, right? So I'm just considering the first medium as first medium's refractive index as n1, and second medium's refractive index is n2. Now, the curved surface formula gives that n2 minus n1, sorry, n2 by v minus n1 by u is equals to n2 minus n1 by r. So r is this, here we can see this curvature, right? So this curvature's radius of curvature, okay? So this is the formula for curved surfaces, and only applicable to, only for curved surfaces, okay? Why it is not be applicable to plane surfaces? Because only for curved surfaces. Why it is not applicable means, here, if let's just take a plane mirror, okay? So plane mirror, this is the coated surface and this is the reflecting surface, and here r is infinity, right? For plane mirrors, radius of curvature is infinity. So let's just substitute this r value in this formula. Then it becomes n2 by v minus n1 by u is equals to n2 minus n1 by infinity, right? So if anything by infinity, that becomes 0. So here we remained with n2 by v is equals to n1 by u. This is for plane mirrors, okay? Plane surfaces we can consider, and this is only for curved surfaces. Got it? Now, let's discuss surface spherical lenses. To call an object as a lens, it needs to satisfy two conditions. So, the first condition is the object has to be made with a transparent material. Then only the refraction can occur, right? So, it should be made of a transparent material. Transparent material. And second one is, so both the surfaces or at least one surface of the object A should be curved, okay? At least one curved surfaces, one curved surface should be there, right? So that is why we have defined lens like this. A lens is formed when a transparent material is bounded by two surfaces, okay, of which one or both. Either we can have a two curved surfaces or at least one. One is the mandatory curved surface should be present in a lens. So on that basis, we have different types of lenses present in the market. So that from that, we here we are going to discuss a few lenses. So the first one is, here you can see the first one is both the surfaces are convex, right? And here if the light if you consider the curvature, both curvatures are equal, so we can call this surface this lens as bi convex lens, okay? Biconvex lens. And the second one, if you see this side, then it is plane, right? And this side it is convex, so it is called as plano-convex surface, I mean lens, fine. And the third one, if you consider the first surface, then it is concave surface, right? So this side is concave surface and this side is convex surface, so we can call it as concavo-convex, concavo, convex. Fine. And these three lenses are known as converging lenses. These three lenses are called as converging lenses. You'll get to know why why these are converging lenses after a few minutes. Okay, and coming to the next case, that is here. If you see, it is a concave surface, and this side also we have concave surface. That too, if you consider, if you observe it, both the curvatures are equal, right? So that both have the same, both curvatures have same focal length. So we call it as bi. Bi indicates two, number two. So biconcave lens. Okay. And the next one, if you observe it, next one, it is the plane surface, and this is again concave surface, right? So we call it as plano-concave lens. Plano-concave lens. And the next one, if you observe it, here you can see one side is convex and another side is concave, right? So we can call it as convexo-concave. And these three lenses are known as, all the three lenses are diverging lenses. Okay, and now let's see how these lenses formed. Anyway, in the whole chapter, we are going to consider, whenever we are discussing about convex lens, we are considering biconvex lens and also here biconcave lens. Okay, these are the two default ones here. And now how this two lenses are formed. For this, we just need to take two transparent spheres of different radius or the same radius. That's not an issue. So one is this radius I have taken, and another sphere I have considered like this. Okay. So this is, these two are transparent. These two are transparent spheres, right? Now, when these two intersect, we are getting, if you observe it clearly, the middle, this shape is nothing but convex, convex lens. Okay, and if you take, then why? What about concave lens? If you consider one more sphere, but it should not intersect with each other, but we need to make it very close, but make sure that these two are not intersecting. Okay, now I have considered this is of one-sided, one more lens. Okay, one more spherical transparent uh, sphere, and if you keep it close, then you can see this shape between them, right? So this is known as yes, concave lens it is. Now the terminology is that here, if you consider, if you take this curvature, then this is the center of curvature. Okay, and if you take this curvature, then for this curvature, this is the center, right? So for this lens, okay, C1 and C2, two centers will be there for a lens, and also two radius, and this is the point exactly, the point at middle point, the point lies at middle of the lens is known as optical center. Okay, there in the spherical lenses, we have known this point on the mirror is known as pole, right? Here it is optical center. Fine. And the distance, the line joining centers and this optical center is known as principal axis, same as spherical mirrors. And here too, the distance from center to the optical center to the center of curvature is known as radius, and the midpoint between these two is focus, right? And the same goes for concave lens too. Here the midpoint here is known as optical center, and for this curvature, and yes, this is the center, and for this curvature, yes, it is the center. Yes, we can consider any one as center 1 and center 2. That's not an issue. And the line passing through these two centers is known as principal axis. Fine. And this is one radius and it is another radius. If we consider it as focal length, focus point, this is another focus point, right? Okay. From this, what we have understood is a lens have two centers, two center of curvature, okay, and two radius, two radii, and also two foci. So two focal lengths and two focus points, right? So that is why we can say it as two focal lengths we have, focus points we have. So this is about formation of lenses. And now we are going to discuss the behavior of light rays when incident on a concave lens and also convex lens. Now, before drawing these diagrams, I just want you to remind that, recall that, for example, if this is the lens, right? It is convex lens. Now you can expect a question like, by closing your eyes, will you identify the lens by touching it? Okay, so you can expect the question like, identify the lens only by touching it without seeing. Okay, so in that case, how do you identify just by touching the lenses? So there is one logic that here on the middle of the convex lens, it is very thin, right? But if you see the sides, it is very uh, thin. Sorry, here it is thick. Okay, so middle of the convex lens is very thick and the edges are very thin. But if you consider concave lens, so middle, it is very thin, but the edges are very thick. Okay, edges are very thick. So this is the difference and the logic you can remember. And one more point is that when we are drawing the ray diagrams, we consider this as with this arrow. Okay, and we consider this, we represent this concave lens as this. Okay, don't get confused when you are drawing the ray diagrams. First, I am first considering that if a ray is parallel to the principal axis, okay, parallel to principal axis, then what happens? Here, if it is a concave lens or a convex lens, I'm taking two cases. And here, yes, so here I'm just taking the principal axis. Yes, for this, it is the principal axis. Now, just locate the points. This is optical center O and focus 1, center 1. Optical center, optic focus 2 and center 2, right? Now the ray incident on this parallelly, okay, parallel to the principal axis. So after incidenting like this, then it always diverges, right? So diverges, and that too, it looks like it is traveling, going through the focus. Okay, and here too, if it is optical center and this is focus and it is center, and here too it is focus and it is center. Now the line is incidenting on this line parallelly, then it looks like, and it passing through the, it always refract through the focus. Okay, this is the first case. And the second case is that if a ray is, second case, if a ray passing through focus, okay, passing through focus, then what happens? Then the refracted ray will be parallel to the principal axis. Okay, parallel to principal axis. Now I'll just show you one case. So that is, I'm considering here convex lens, and this is optical center, and yes, it is the focus. Okay, so focus and this side it is focus, and yes, it is center, right? Now the light ray is incidenting on this lens like this. Okay, now it is incident ray is passing through the focus, right? After refraction, the refracted ray passes parallel to the principal axis. Okay, the same goes for convex lens too, concave lens too. And the third point is that if the ray is passing through optical center, if the incident ray is passing through optical center, then diffracted ray will be in the same path, non-deviated. Will get a non-deviated ray. Okay, so I'll show you how it is. So this is our convex lens, right? Now this is optical center. Now if a ray is going like this, if a light ray is going like this, then it, without any deviation, it refracts to the lens. Got it? And the same goes for concave lens too. So these are the behavior of light rays when going from a lens. Now, by this, on this basis, we are going to discuss one more important point, that focal plane. So what is this plane? Simply, this is the plane. Okay, a plane perpendicular to principal axis and having focus point on it. So here you can see it is the focus. Okay, now if you just consider this plane, then it is known as focal plane because it is perpendicular to the principal axis. Okay, and also this plane has focus on it, right? So this plane is known as focal plane. So when the image forms on this focal plane is, so when a parallel beam of light falls on a convex lens, so then what happens, this convex lens converges all this parallel beam into a single point, right? So but if these parallel lines are going incidenting on this convex lens obliquely, that means here you can see all these rays are making some angle theta with the principal axis, right? In this case we can expect the all these rays in converges, that is for sure, but all these rays converges on the plane which is parallel to the principal focus, right? So that plane is known as focal plane. And let's see the images formed by the convex lens first. For that, we are considering the infinity case. When we place the object at infinity in front of a convex lens, then it converges all these parallel rays because just now we have discussed the point that if the incident ray is parallel, then the refracted ray goes from the focus, right? So that is why all these parallel rays get converged at one point on the principal axis, that is focus. So we will get here the object at focus. Okay, object at focus, and also the characteristics. So these refracted rays directly converging at one point, right? So we are getting here it is a real image, and real image always inverted, right? And also if you observe the diagram, you can see the image is point sized, so we can consider that it is highly diminished object. Got it? So these are the characteristics of the image formed by the convex lens when we place the image at infinity distance in front of this lens. Now we are just moving a little closer to the lens, that is the case when we place the object beyond the center. Beyond the center, we can consider that here to the relation applicable, that 2f is equals to r, right? So that is nothing but here this distance is considered as focal length, and this complete distance here we are considering it this point as center, or 2f12. Now we have placed object beyond the center. Now we can take two lines that by your choice it can be parallel or it can be passing through optical center or focus. Now in this diagram you can see the lines are passing. Okay, one line is one incident ray is parallel to the principal axis and another ray is passing through the optical center, right? So the ray which is passing through the optical center, after refraction, its path is same. It won't deviate. But when the incident ray which is parallel to the principal axis, after refraction, it passes through the focus. So when these two rays is extended, then these two rays extended intersect at this point. On this point only we'll get the image. So now the position of the image is between focus and center of curvature, we can say, or else between focus f1 and f2 and 2f2. Got it? And the position, I mean, after position, we can observe the size. So what is the size here? It is little bit diminished, right? So we got diminished image. And what about the image? Is it real or virtual? So since these two direct refracted rays diverge, converging at one point directly, that so that we can get the image which is real. So since the image is real, so it is inverted. And also you can observe from the diagram that so object here is upward, I mean upright, but the image is upside down, right? So here we got inverted image. So these are the characteristics of the image formed by the convex lens when we place the object beyond center of curvature. Now, so the third case is that when we place the object at its center of curvature or 2f1, right? So from here to from point A, here we have considered two incident rays. One is going through the optical center and another is going parallel to the principal axis. As we can draw these lines from the behavior of rays. So the parallel ray goes through the focus, and the incident ray, I mean the incident ray which is going through the optical center will be undeviated, right? So here when we intersect, when we observe the intersecting point, it is exactly parallel to the 2f2 point. So that is, we can consider it as a center, or at 2f2 we can consider. When we place the object at 2f1, we got the image at 2f2. And if you observe the size, it is same sized image we got, right? Same size, image of same size. And is it real or virtual image? So yes, of course, two refracted rays directly converged at one point, right? So we got real image, and from the diagram you can say that it is an inverted image. Got it? So these are the characteristics. And the fourth one is we just moved from 2f2 to between 2f and f. So now, I mean, you can consider the object placed between center of curvature and focus. Okay, it's not focal length, it is focus. Now, so here too, when these two rays incident at when these two refracted rays converged at one point, that is when we take image lines, then that is exactly beyond center of curvature. So we got the image here. So the position of the image is beyond C, beyond center, or else beyond 2F. Okay, and the image size is you can observe it from the diagram, that ray diagram, that it shows the image is magnified, right? So we can write either magnified image or enlarged image, and whether it is virtual or real. So since these two refracted rays converging directly, so we got real image. And yes, real image is always inverted, and that is we can also confirm from the ray diagram. So this is the characteristics of the image when we placed object between center and focus in front of a convex lens, right? Now we are moving the object from this position to the exact at focal length position. So when we place the object at focus, then it is not focal point, it is focal point we can consider, yes, also focus. So now here this point is considered as A. From this point A, we have taken two this is the object So the fifth case is when we place the object at focus, right? So let's try to draw this ray diagram. So first, we are going to consider this convex lens. So that is, so this is convex lens, right? Now we are going to draw a principal axis, and also we are going to locate all these rays. So this is the principal axis and optical center, and also this is focus, this is center, and this side also this is focus and it is center, right? Now if we place the object from, so this is the case that when we place the object at focus, right? So here I'm considering the object, and also from this point I'm just considering two rays which are parallel to the principal axis and also which is going to the, so one is parallel to the principal axis and the another ray which is going directly through the optical center. Okay, so the ray which is going through the optical center, it is undeviated, and also one more ray that is parallel to the principal axis, it goes through the focus, right? So from this point, these two are going like this. So we got two reflected rays like this. If you observe this carefully, these two are parallel, right? So these two rays, I mean refracted rays are parallel to each other. So if we need to get the intersection of these two lines, then we have to extend them to the infinity, right? So there we can expect the image. So what is the characteristics of the image in this case? Firstly, the image is placed at, the image is formed at infinity, okay? And at infinity, the image size is highly enlarged, or else highly magnified, okay? And what about the image? Is it real or virtual? Since these two refracted rays converging directly, so it is a real image and also inverted image. Okay, we can expect inverted image in this case. And final case, that when we place the object within the less than focal length, so that is between focus and optical center. So in this case, we will get the diverged rays. Okay, so here we won't get, here the refracted rays are diverging. Fine. So we are extend. So there is no chance that even if we extend to the infinity, there is no intersection of these two lines, right? That's why what I'm doing, I'm just extending these two rays in the backward direction so that these two are intersecting at this point. At this point, I can expect, at this position, we can expect the image. So what is the position of the image formation in this case? It is beyond C. Beyond C. And also the image is highly enlarged and magnified image we got. Magnified, and then the image is virtual in this case because these two lines are not directly converging. We are diverging, we are just extending the divergent rays in the backward direction, right? So we got the virtual point. At this point, it is the virtual image we got, and this virtual image is always erected. So these are the characteristics of the image formed by the convex lens when we place the object between focus and the object, right? And the next cases, these are the 6 cases we have completed of for the lens convex. So now it's time for concave lens. So concave lens, we don't have 6 cases, we only have 2 cases. That is at when we place the object at infinity distance and also at finite distance, same as convex mirror in spherical mirrors. So concave mirror is similar to convex lens, and convex mirror is similar to concave lens. So here, if you can observe this, so since it is a diverging lens, all the parallel rays get diverged like this. But if you extend this in the backward direction, all these rays appear to be diverging from this particular point, right? So here we will get the image, but it is a virtual image. So what is the position of the image at focus? that is fine. But this image is, we're not getting the direct refracted rays get converged, right? So these reflect, we are getting this image by the divergent rays, so it is a virtual image. And also, if you observe the size, it is very point sized object, so it is diminished highly diminished. And is it inverted or erected? So we can't exactly say it from the diagram, right? I mean, from this ray diagram. So we can use this point as a clue. So virtual image is always erected. So these are the characteristics in this case. And the next case is when we place the object at finite distance. Finite distance, you can consider any. It can be beyond focus, beyond center, or at center, between center and focus, anywhere. But all for all these places, you'll get the object at only this single place, that is between focal length. I mean, between focus and optical center. Okay, so that image is, so image play located at between focus and optical center. And this image is virtual image because it is this lens is diverging lens, right? So we'll always get diverging rays. So if we extend this diverging rays in the backward direction, these two are appear to be diverging at intersecting at this point. So at this point we'll get the image. So that is why it is a virtual image. And virtual image is always erected, right? And also that we can confirm it, we can confirm from the diagram. Okay, so it is erected. And also one more point is that the size. What about the size? So it is the object and this is the image. So this image is image size is decreased, height is decreased, right? So here we got diminished image. So of all these points, I mean cases, what you have understood. So here mainly focus on if we talk about convex lenses. Convex lens always forms the real image and inverted image, except one case when we place the object within the focus and optical center. Only in that case we get virtual image, and that too magnified. But when it comes to concave lens always gives virtual image and erected image, but in this case, virtual image always diminished. Got it? So these are the 6 cases of concave, convex mirror, and also 2 cases of concave mirror. Lenses it is. And when it comes to convex lens and concave lens. Convex lens, we use it for to magnify the objects, right? So what are the uses? So we use it in magnifying lenses. Okay, magnifying lenses, glass, and also binoculars. Okay, binoculars we will use it, and also spectacles. So there are few defects of vision. So in that we use it to correct hypermetropia. Okay, correct defect of vision. Fine. So these are the uses of convex lens and concave lens. So what concave lens gives? It always gives the diminished image, right? So we need to use, we will generally use it to get the diminished image of the object. So, so the first case is that camera lenses. Okay, camera lenses and door peepholes. Fine. And also we use it in telescopes. Fine. So these are the few uses of concave lenses and convex lenses in our day-to-day lives, right? So after that, there are few important formulas we need to learn from this chapter. So that is, the first one is lens formula. That gives the relation between focal length, optical object distance, and image distance. So that is lens formula. So it says that, what is this formula? So that is 1 by f is equals to 1 by v minus 1 by u. Okay. And also one more important formula we do have in this chapter is, yes, that is magnification. Got it? Magnification m is equals to h I by h naught. It is same for, still here same for spherical mirrors too. But here we don't have sign for this relation. Okay. And here we in spherical mirrors we will get plus, right? But here we have minus. So note this carefully. And the next one is lens maker's formula. Okay. Lens maker formula is generally gives the relation between focal length and refractive index. Okay, I'll tell you where it will be useful. For example, there is a convex lens. Okay, and this is the optical center, and this is object. Here object is located and we got the image here, right? So when a light ray is going from here to here, then it is entering to the in this mediums, right? So the refractive index of this medium is n, and this is the object distance, and this is the image distance, and it has radius r1 and r2 are the radius of this lens. Okay, so in this on this note we can write the relation between focal length and refractive index. So that is 1 by f is equals to n minus 1 into 1 by r1 minus 1 by r2. So this is the formula for lens maker's formula. Okay, so whenever we are writing substituting values in this, we just need to consider the sign convention. So how this sign convention works here? So same as spherical lenses, spherical mirrors, but the say one difference is that sign convention. So here just take any any lens. Okay, and we are considering a principal axis. Here this is optical center, right? So this optical center is known as origin. Okay, all the distances are measured from this origin. If the distances are measured along this direction, okay, are positive. Okay, if the distance is we are finding is measuring is this way, and if it is negative x-axis, then it is negative. And if you are measuring perpendicular and upward distance, then it is positive. But if it is downwards, then it is negative, right? So now on this case we can consider that concave. Okay, concave mirror lens it is, and this curvature, so object is placed here, and this is the light ray incidenting on this. So this curvature's focal length is this side, right? So if I measure this focal length, then it is positive. So concave lens's focal length is, convex lens focal length is always positive, and concave lens, okay, this is concave lens. And for if light ray is incidenting like this, then this is the focus. So from this is optical center. So this is direction is negative. So focal length of concave lens is negative. Okay, so remind this formula, I mean the sign convention. So guys, this is all about the refraction of light at curved surfaces, that means lenses. So I hope you have understood this chapter. We'll discuss the next chapters in our next session, that is human eye and colorful world. If you have any doubts from this chapter, then do let me know in the comment section and subscribe this channel. And if you have any kind of doubts, not only from this chapter, from the whole 9th and 10th class physics and maths, you can clear from this chapter. Okay guys, we'll meet in the next session. Till then, keep learning and bye.